Now, welcome to all of you to the fourth class of interference. In this class, we have to study what is Stokes treatment and interference in thin films by reflected light. Now, according to this Stokes treatment, wave on reflected from the denser medium gets accelerated by distance is equal to lambda by 2 or in phase increases by pi. So when wave is traveling from rarer medium to the denser medium, falls on the surface, this species is a reflected wave. It is accelerated, means its path increases by lambda by 2. Now this we have to prove. This is important. Let initially, this is A is the amplitude of the wave falling on this denser medium, surface separating the two medium. And let R and T are reflection and transmission coefficients. What is this reflection and transmission coefficients? The amount of light reflected divided by the total amount of light falling. What is transmitted? Amount of light transmitted divided by the total amount of light falling is called as the reflected and transmission coefficient. Then reflected amount of light is A into R. Then transmitted amount of light is A into T. If this BC is reversed according to the principle of reversibility, if this BC is reversed, amount of light falling at B is AR, part of it gets reflected. How much amount is reflected? Falling is AR and again R. Then part of this is entered into the second medium. Here amount of light entering is AR into the transmission coefficient here T. Now BC gets reflected. Similarly, if this BD gets reversed, amount of light falling here is AT and some part is reflected here. So the amount of light reflected is AT R dash. What is AT R dash? What is R dash? It is reflection coefficient from the lower side. And you know that part of this light also goes to the second medium, this medium. Amount of light falling is AT. Here it is transmitted. Now this is A, T, and it is T dash. If there is no loss of this light energy, the sum of these two should be equal to A. Means it is A T T dash plus A R R should be equal to incident wave of amplitude A, because this wave has started. But what about sum of these two? Sum of these two should be definitely 0. Means here ART plus ATR dash should be equal to 0. Or this is ATR should be equal to minus of ATR dash. And this AT get cancels. R is equal to R dash, negative. R is equal to R dash means what? The wave has reversed its direction. So thus, according to Stokes treatment, the wave on reflection gets accelerated by distance equal to lambda by 2 or by phase equal to pi. Then after that, you have to study this interference in thin films by reflected light. You have to remember this: if the light is reflected from the denser medium, it is accelerated by lambda by 2. If it is reflected from the rarer medium, there is wave is not at all accelerated. Now, interference in thin films by reflected light. They will ask this as a 10-mark question. See, consider this is a denser medium of refractive index greater than 1. A wave is traveling from rarer medium to the denser medium. SA is the incident wave with an angle of incidence I. Now here two things takes place: part of the light is reflected and part of the light is transmitted. This phenomena is known as reflection. It's sent back into the same medium. Part of the light enters into the second medium by changing its direction. It is called as refraction. See, one wave goes along AR1. Then the wave travels along AB. It has to transfer from denser medium to the rarer medium. Then part of the light is transmitted here and part of the light is reflected. Then once again at point C, the ray is traveling from denser to the rarer. This is refracted light and this is reflected light. C and N, the wave CR2 and NR1 have derived from the same monochromatic source, yes. So here is a monochromatic source. These R1 and R2 came from the same source. Definitely these two are what? Coherent sources. Then interference fringes observed in the path of emergent beam AR1, CR2. The question is whether constructive interference takes place or destructive interference takes place. You know that it depends on the path difference. Now we have to obtain an expression for path difference P. So between the two rays, see here, from N and C, both the waves are traveling with the same distance. But the wave which passes the C has traveled an extra distance along ABC. Then it does, if you consider from N and C, this wave has got an extra distance AN. That means your path difference P is a path along ABC in the denser medium it is, plus another extra path difference is AN. Or this is optical path difference is mu is equal to mu into AB plus BC is ABC plus AN. Call this equation as 1. Now, we have to find that figure what is AP, what is BC and what is AN, and then you substitute here. See, this is normal drawn at point A, and here BM is normal drawn to the boundary surface. I is the angle of incidence, R is the angle of refraction. This angle and this angle are same because they are between the two parallel boundaries alternate angles. And if this is I, this is also I, because the law of reflection, angle of incidence is equal to angle of reflection. See, from the figure, AB upon BM AB upon BM. If this is R, this is hypotenuse side, and this is adjacent side. AB upon BM is 1 upon cos R, because BM upon AB is cos R. From this, what is this AB? Is BM upon cos R. What is BM? This BM is nothing but T. This is AB is equal to T upon cos R. But you know that AB is equal to BC. AB is equal to BC. Therefore, this AB plus BC is equal to T upon cos R plus T upon cos R. This is 2T upon cos R. Next, you have to find what is this AM. This AM. See here, this angle I and this angle. Total it is 90, and this angle becomes 90 minus I. See, follow, this is the right angle triangle. This angle is I. This angle is 90 minus I. Then this angle plus this angle plus this angle is 180. Assume that this angle is x. Take this angle as x. So 90 minus I plus 90. Plus 90 means this plus x is equal to 180. Or from this equation you can get this as x is equal to I. That means the angle, this angle, instead of yes x, it becomes I. Okay. If that angle is I, right angle triangle ANC, AN upon AC is what theta? Opposite side divided by hypotenuse is sin theta. This is sin I, or this is AN is equal to AC sin I. What is this AC? AC is AM plus MC. AM plus MC into sin I. So AM is same as MC. AM is same as MC. AM upon MB or AM upon BM. Opposite side divided by adjacent side is tan theta. This is AM upon AM upon BM is equal to tan R, or this is AM is equal to your BM into tan R. What is that BM? BM is nothing but thickness of the denser medium, or this is T into tan R. Then AM is equal to MC. AM is T tan R, this is also T tan R. Then substitute in that equation your AN, this is AN is equal to, this is T tan R plus T tan R into sin I. This is 2T tan R into sin I. This is 2T sin R upon cos R. Into sin I. Multiply both the numerator and denominator by sin R. This is sin R upon sin r. You know that this sin I upon sin r is a Snell's law, which is a refractive index. Therefore, I can write this is 2 mu t. What is remaining here? Sin square r sin r into sin r divided by cos r. This is your an. Now substitute the value of AB, BC and AN in this equation 1. You will going to get this as, so your AB plus BC is 2t upon cos r. You write this is mu as it is and into 2t cos r. Sorry, 2t upon cos r it is. 2t upon cos r plus an is 2 mu t sin square r sin square r upon cos r. Then after this, take 2 mu t cos r outside. This is 2 mu t cos r. What remains inside the bracket is 2 mu t cos r is taken outside, it is 1 plus 2 mu t cos r sin square r, and this is equal to, it is cos square r 2 mu t upon cos r into cos square r. This cos square r get cancelled with that one. Therefore, your path difference is 2 mu t cos r. Call this equation as 2. But you know this, according to Stokes treatment, this reflected ray has covered an extra path of lambda by 2. Therefore, that lambda by 2 has to be subtracted. You know, according to Stokes treatment, the light you have reflected from the denser medium is accelerated by lambda by 2. Therefore, this path is P is equal to, actual path is 2 mu t cos r minus lambda by 2. This is your, call this equation as 3. This is your expression for path difference. Then you know that whether a constructive interference takes place or destructive interference takes place, it depends on the path difference. So if your P is equal to n lambda, means path difference is equal to n lambda, bright fringes are obtained or it is constructive interference. Therefore, this equation is n lambda is equal to 2 mu t cos r minus lambda by 2. Then 2 mu t cos r is equal to, it is n lambda plus lambda by 2. Then you take this lambda by 2 outside, your path difference becomes q 2 mu t cos r is equal to, it is lambda by 2 is taken outside, this becomes 2n plus 1. So here, if you multiply this lambda by 2 to this one, this is lambda by 2, means 2 to get cancelled, it is n lambda, then this is lambda by 2. This is equation 4. So equation 4 represents the condition for constructive interference. Then what is that destructive interference? If this equation 3 is equal to 2n plus 1 lambda by 2, that means for destructive interference, if p is equal to 2n plus 1 odd integer lambda by 2, condition for constructive interference, then this becomes, it is 2n plus 1 lambda by 2 is equal to 2 mu t cos r minus lambda by 2. Then what is this 2 mu t cos r? 2 mu t cos r is equal to, it is 2n plus 1 lambda by 2 plus lambda by 2, and this is nothing but here lambda by 2 into n, it is n lambda plus lambda by 2 plus lambda by 2, and it is lambda n lambda plus lambda, or this is, it is, if you take this lambda outside, n plus 1, again n plus 1 is an integer. If you put n is equal to 0, it is lambda, n is equal to 1, 2 lambda, n is equal to 2, 3 lambda, or in other words, this is your 2 mu t cos r, I can write it as n lambda only. This is the condition for destructive interference. So in the examination, they will ask, obtain the path difference in the case of reflected light and arrive condition for constructive and destructive interference. You have to write up to this. See, we have first obtained path difference between these two waves in the case of reflected system, and we have considered the Stokes treatment, means if a ray of light is reflected, so we have first derived the path difference between the two waves in the case of reflected system, that we got P is equal to 2 mu t cos r. Then we have applied this Stokes treatment such that in the case of reflected system, from the denser medium, the ray gets accelerated by lambda by 2. By considering this, we have written the exact path difference P is equal to 2 mu t cos r minus lambda by 2. Then we know the condition when the constructive interference takes place and destructive interference takes place. we have used the condition for n lambda, we got this is the condition for constructive interference. And after substituting this 2 mu t cos r minus lambda by 2 is equal to 2n plus 1 pi by 2, we got this equation, destructive interference. This is in the case of reflected system. But in the case of transmitted system, that means these rays transmitted here and these two appears to come from the single source, then interference pattern observed here also. That is the transmitted system. But in the transmitted system, the path difference lambda by 2 never occurs, because this is true only in the case of reflected system. Therefore, for transmitted system, your path difference is as it is 2 mu t cos r. Here we cannot apply that Stokes law. Then for constructive interference, this path difference is equal to n lambda. That means this is 2 mu t cos r. This is constructive interference. And for destructive interference, the path difference is 2n plus 1 lambda by 2. This is what 2 mu t cos r. This is for destructive interference. Observe call this equation as 6 and this as 7. Observe these equations. Equation 4 represents the condition for constructive interference. Equation 6 represents condition for constructive interference. This is in the case of reflected system and this is in the case of transmission system. Then this equation 5 is same as equation 7. Means here it is destructive system and this is also destructive system. So this shows that this transmitted and reflected systems are complementary. That means a band which is bright in a reflected system, the same band appears as dark in the transmission system. Again here also, this is a band which is dark in reflected system appears as bright in the transmission system. Means if there is a dark band, so light energy decreases, and if there is a bright band, light energy increases. So which is known as the law of conservation of energy. If a thin film is illuminated by white light, for example, consider a beaker containing water. Then on the surface of this water, assume that the thin film is formed due to an oil. Oil is poured. Then if this is illuminated by white light, and observer from one point observes the surface of this thin film, he finds a colored rings observed on the surface. What color is observed? Why this happens? It is simple. White ring consists of different colors, and when it falls on the surface of the thin film, the different colored rings are produced. Then the particular color depends on the position of the eye, in other words, inclination, and a particular point which is observed. And also, it depends on thickness of the film. So, colorization depends on the position of the eye and also point at which we are observing, and the thickness. If the thickness goes on changing, colors also goes on changing. So, if position of the eye changes, at the same point the color also changes, because the path difference between the two waves satisfying the maximum condition, maximum intensity condition changes, and you are going to observe the other colors. So, this colorization on the thin film is mainly due to interference.